Hi everyone, sorry this took me so long. So this is the last Chem1 mock that you did, the run through of that. So the first question asks you to define the term relative atomic mass. This is going to be on one of your flashcards, and it's a standard definition. So it's the average mass of one atom of an element divided by 1/12 of the mass of one atom of carbon-12. Now, the word that generally students miss are the average, one atom, because if you just put the average mass of an element, you haven't said how much, and they miss an atom of carbon-12 down here as well. Sometimes students just put the 1/12 mass of carbon-12. You need to make sure you say how much of each one, so all of those words are all important there. The next question asks you to use this data up here to calculate the relative atomic mass of X. So you're going to do 70 times 3 plus 72 times 4 plus 73 times 1 plus 74 times 5 and divide that by 5 plus 4 plus 1 plus 3. So the relative abundance times the MZ values all added together. So 70 times 3 plus 72 times 4 plus 73 times 1 plus 74 times 5 divided by 3 plus 4 plus 1 plus 5. And that gives you an answer of 73.38. But in the question, you have to do it to one decimal place. You will lose one of the marks if you don't. So the answer is actually 73.4 to get the 3 marks. Now if they ask you to identify the ion responsible for a specific peak, they want a lot more than just the element that is causing it. So the element, if you look up the 73.4 that you worked out in the previous answer, you'll find that's germanium. And then the ion responsible is germanium 1+. And actually, you could give that a mass number as well, seeing it's the peak at 72. Okay, so germanium 1+ is what you need to put there. Identify one of the isotopes of X that deflected the most in a magnetic field of mass spectrometer and give a reason. So this is the one with the MZ value of 70, and that's because it's the lightest. So the lightest one is going to be deflected the most. In a mass spectrometer, the relative abundance of each isotope is proportional to the current generated by that isotope of the detector. Explain how this current is generated. So, it's the idea that electron is transferred. So you get your 1 mark, and then just saying where it goes from. So from the detector to the ion. Okay, and because of that, that causes an electron flow. And some of you are putting things like the current that's produced is proportional to the abundance. Well, that's actually already in the question, so you don't get any marks for that, but it's good that you recognise that. But how it actually happens is what you got the marks for in this question. But sometimes you will get marks for saying this if it's not in the question itself. This next question is kind of a rehash of a question that is often asked. So explain why the chemical properties of these two are different. Usually it's asked, the question is explain why the chemical properties of isotopes are the same. But this one is asking why they're different, and this is because they have different electron structures. So not the same electron structures, like when you're explaining why chemical properties are the same. Here you have different electron structures. Okay, next question. So the hydrocarbon but-1-ene is a member of the homologous series of alkenes. But-1-enes has structural isomers. What's the meaning of the term structural isomers? So first mark, so we're saying that they have the same molecular formula. And the second mark is saying that they have different structural formula. Then give the IUPAC name for the position isomer of but-1-ene. So in position isomers, you're changing the position of the functional group. So you can move that double bond along one between the second and the third carbon, so but-2-ene. And the chain isomer of but-1-ene, well, if we draw but-1-ene up here, a chain isomer is going to shorten the longest chain. The longest chain here is 4, so we need to make the longest chain 3 instead, and then have a carbon coming off. So that's going to be methyl on the second carbon. So 2-methyl propene, because there's 3 carbons along this chain. Now actually, you wouldn't need that 2 here because you can't have that carbon anywhere else for it to be a chain isomer of propene. So actually, methyl propene would have been fine there too. Draw the display formula of the functional group isomer of butadiene. Well, you're only ever going to ask one functional group question, functional group isomer question in Chem 1, and that is between alkenes and what the functional group isomers of alkenes are, and that is cycloalkanes. So this is what you need to draw, and you need to make sure you drew all the bonds because they've asked you for the displayed formula. So that means drawing every single bond out. So if they ask you for the displayed formula, you must make sure you provide them with one. If you don't draw one of the bonds and draw it as a kind of a structural formula instead, you will lose that mark because you haven't done what they've asked you to do. Butadiene burns in a limited supply of air to produce a solid and water only. Write an equation. So butadiene is C4H8. It's reacting with oxygen, and it's making a solid, which is the carbon, so soot, and water. They need to balance it. So to balance, you need 4 waters, 4 carbons, and 2 oxygens. State 1 hazard. So that can exacerbate. Don't know how to spell that. Let's change it. Make asthma worse. So the idea that the soot can cause respiratory problems if it's breathed in, or it can make asthma worse is good there. And then 1 mole of a compound Y is cracked to produce 2 moles of ethene, 1 mole of butadiene, and 1 mole of octane only, and deduce the formula of Y. So basically, you've just got to add up these to work out what Y must have been to begin with. So it's going to be 2 lots of ethene, so 2 lots of C2H4, 1 mole of butadiene, so that's C4H8, and 1 mole of octane, which is C8H18. So what that gives is, so you've got 2 lots of C2 there, so that's 4, 8, 16, so it's going to be C16, and then you've got 2 lots of H4 here, so 8, 16, and then that's 34, so C16, H34, and what I would do is just cross out your working there, because all they want is the one formula. Then other than cracking, give one common use of Y. Well, you can burn it, so it's a fuel. It's not petrol though, petrol's a lot shorter than the C16, but it can be, so fuel will be fine there. It's just a general use. In cars fitted with catalytic converters, unburned octane reacts with nitrogen monoxide to form carbon dioxide, water, and nitrogen only. Write an equation. So you've got unburnt octane, so C18H18, and that's reacted with nitrogen monoxide, so NO, and you'll be making carbon dioxide, CO2, plus water, plus N2. Then you just need to balance that. So you're going to need to have 8 carbons, so 8 carbon dioxides, 9 waters, and then you need to balance your oxygens from there, and then balance nitrogens at the end. So you've got 8 lots of 2 oxygens here, so 16 plus 9, which is 25. So you need 25 over 2 nitrogens, so nitrogen oxides, and then therefore 25 over 4 N2s. Then identify a catalyst used in a catalytic converter. So platinum is your easiest one there, but you can also have rhodium, palladium, I think. Next question. In 2009, a new material called graphene was discovered. Here it is. There's a picture of it. So deduce the type of crystal structure shown. Well, you can see there's lots and lots of covalent bonds here, all joining it together. So that is giant covalent. And then it says, state how 2 carbon atoms from a carbon-carbon bond, in how they're joined in graphene. So that's they share, I spelled share wrong, it's late, share a pair of electrons. So not just share electrons or share a share of 2 electrons, because they share a pair of electrons. The word pair is really important. Just why it doesn't conduct electricity, if you ever get asked this, it's just because it doesn't have delocalized electrons that can move, if you want to add that, but the fact delocalized electrons, the word delocalized suggests they can move, so just putting they don't have delocalized electrons is fine. Then the empirical formula, a lot of people struggle on this. For every one carbon, there's one hydrogen attached to it. And that's the same all the way along it. So actually this is just CH. So a lot of people were putting C3H because you could see that each carbon is also attached to 3 Cs. But if you included those 3 Cs as well as attached to, you need to include the 3 H's that are attached to those Cs as well, which would give you C4H4, which you can then simplify back down to CH. So that's why that's the empirical formula there. Fritz Haber, a German chemist, first manufactured ammonia in 1909. Strongest type of force, well, it's NH3. So you've got H attached to an N, so you've got hydrogen bonding there. And then draw a diagram to show how one molecule of ammonia is attracted to one molecule of water. So ammonia is the following, NH3. And then you've got water, which is H2O. A few of you are drawing 2 O's and 1 H. Okay, so just make sure you got that right. And then remember for hydrogen bonding diagrams, your number of bonds and number of lone pairs should add up to 4 on each molecule. So you've got 1 lone pair on the nitrogen there, and 2 lone pairs on the oxygen of the water. Then you need your delta pluses on the hydrogens, and your delta minuses on the N and the oxygen, and then you need the attraction between the lone pair on the N and the H. Equally, you could have done the attraction between the lone pair on the O and an H on the ammonia, but it doesn't matter which way around you do it. Phosphine, pH 3, has a similar structure to ammonia. In terms of intermolecular force, suggests the main reason why phosphine is almost insoluble in water. So this is because it cannot form hydrogen bonding. And that's because the phosphorus isn't electronegative enough. Aluminium and thallium are elements in group 3 of the periodic table, both elements from compounds and ions containing chlorine and bromine. Write an equation for the formation of aluminium chloride from its elements. So you've got aluminium as one element, Cl2, chlorine for the other element, and then aluminium chloride. It's in group 3, so it just needs 3 chlorines to complete it. Well, it can only share 3 more electrons, so it's AlCl3 is your formula for that. So you can put 2, 2, and 3 to balance that. An aluminium chloride molecule reacts with the chloride ion to form AlCl4- ion. Name the type of bond formed and explain how this type of bond is formed. So it's a dative bond, and any group 3 element is going to have a space where a lone pair can be donated into to form this dative bond. So it's the Cl- here that's donating the lone pair, the chloride ion. So you can say the Cl- donates a lone pair to the AlCl3 if you want, or just the Al. But you've got to say what's donating it, say it donates it, and then what it's donating it to. But make sure you say it's donating a lone pair, not just it donates electrons. Aluminium chloride has a relative molecular mass of 267 in the gas phase. Deduce the formula of the aluminium compound as a relative molecular mass of 267. So this is Al2Cl6, because the two AlCl3 molecules can join to form this bigger molecule, Al2Cl6, which gives you 267. Deduce the name or formula of a compound that has the same number of atoms, the same number of electrons, and has the same shape as the AlCl4- ion. So if you move across 1 in the periodic table from aluminium, that gives you silicon. So that gives you 1 extra electron there. And then that means you don't have to have a negative charge when you put Cl4 there. So that's your answer there. Draw and name the shape of the TlBr5 ion. So thallium is in group 3. So you've got 3 electrons from that, you've got 5 bonds, and you've got 2 more electrons from the 2 minus charge. So add that up, that adds up to 10, divide by 2, that gives you 5. So that means that this is going to be based on a trigonal pyramidal shape. So you've got TL, and then no lone pairs, just bonds like so, and that is called trigonal by pyramidal. And then draw the shape of the TL of the thallium chloride ion. So you've got 3 from the thallium, 2 from the 2 bonds, minus 1 from the 1 plus charge. So that adds up to 4. Divide by 2 equals 2. So that just looks like this. It's just a linear shape. Explain why the TlCl2 plus ion has the shape that you've drawn. So when you're explaining why shapes occur, you say how many bonds there are, so 2 bonds, and then you say that they equally repel. And therefore they try and get as far away from each other as they can. Which one of the first, second, or third ionizations of thallium produces an ion with that electron configuration? Well, thallium is in group 3, so the full electron configuration is going to be 6s2, 6p1 if it's in group 3. Now, to form this configuration, it needs to have lost that electron there and one of those two, so that's 2 electrons. So the second ionization is going to give you that configuration. The elements in period 2 show periodic trends. Identify the period 2 element from carbon to fluorine that has the largest atomic radius and explain your answer. So remember, atomic radius decreases across the period. So the largest atomic radius from carbon to chlorine is going to be carbon. And that's because carbon has fewer protons in its nucleus, so it has the lowest nuclear charge, but it has the same electron shielding as all the others. Then it says, state the general trend in first ionization energies from carbon to neon, deduce the element that deviates from this trend and explain why this element deviates from the trend. So the general trend in first ionization energy is that it increases. But one from carbon to neon dips down, and that's oxygen. And the reason is that oxygen, it has a pair of electrons in its 2p orbital. So you've got to say where they are. So not just p orbitals, you've got to say the number as well. So 2p orbitals, and then you've got to say that they repel each other. Then write an equation including state symbols for the reaction that occurs when the first ionization energy of carbon is measured. So carbon, it's got to be a gas, turns into carbon, positively charged, a gas, and also an electron is given off as well. An electron you'd have to put the state symbol on, because you can't have gaseous electrons, or liquid ones, or solid ones. Explain why the second ionization energy of carbon is higher than the first ionization energy of carbon. That's because electron is more attracted to the positive ion. Okay, if something's positively charged, that's going to be more attractive to the electron than something that's just neutral. And then deduce the element in period 2 from lithium to neon that's this highest second ionization energy. And this is a bit of not a trick question, it's a tricky one. So what you've got to think about is if you take an electron away from lithium, that's going to be the outer shell electron. So the next electron you take, i.e. the second ionization, is going to be from the shell further in. So that's why lithium has the highest second ionization energy from those elements. Okay, so on to moles questions now. So zinc forms many different salts, including zinc sulfate, zinc chloride, and zinc fluoride. People who have zinc deficiency can take hydrated zinc sulfate, it has a dietary supplement. A student heated 4.38 grams of hydrated zinc sulfate and obtained 2.46 grams of anhydrous zinc sulfate and used data to calculate X. She's trying to work out how many waters are associated with it. So this is an empirical formula question. First thing you've got to do is work out what mass of water was in this amount of zinc sulfate. So it tells you that you got that much zinc sulfate out of it, so the amount of H2O is going to be 4.38 take away 2.46, so that equals 1.92. They need the MRs of both of the parts of the zinc sulfate with the water. So the MR of zinc sulfate is 161.5, and the MR of water is 18. So you just divide these two numbers by the MRs, so just like you would if they're just elements. So you've got 2.46 divided by 161.5, and you've got 1.92 divided by 18, and then that gives you two numbers. So that's 0.0152 and 0.107. Divide by the smallest number, and that gives you a ratio, so 1 to 7. So therefore x equals 7. Make sure you finish your answer by answering how the question asks you to state what x is. So make sure you do. X equals 7. Next moles question. Zinc chloride can be prepared in the lab by the reaction between zinc oxide and hydrochloric acid. The equation for that is this. It says a 0.0830 mole sample of pure zinc oxide is added to this amount of hydrochloric acid. Calculate the maximum mass of zinc chloride that could be obtained. So this is a classic Mr. T question. So first is moles. Well, you've already got your moles. It tells you that you've got that number of moles of zinc oxide, but you've also got this number of moles of hydrochloric acid. So it's probably worth checking which one is the one that's in excess. So you've got moles of HCl, that equals 100 times 1.2 over 1,000, so that equals 0.012. Now, if the amount of zinc oxide that would be needed to react with this is 0.06, so 0.012 divided by 2, because that's what the ratio is. Now we've got more than 0.06, so that means the zinc oxide is actually in excess, and it's this number of moles that we've got to work from to work out our maximum mass that we can make. So therefore our moles of zinc chloride will equal 0.012 divided by 2, which equals 0.06, and then our maximum mass is going to be, so that's the triangle, we've got to use the appropriate triangle, and that's going to be mass equals moles times MR. So your moles is 0.06 times by the MR, which of zinc chloride is 136.4, and then you get 8.18 grams as your answer. So next question, another moles question. Zinc chloride can be prepared in the lab by reaction zinc and hydrogen chloride gas. There's the equation. An impure sample of zinc powder with that mass was reacted with hydrogen chloride gas until the reaction was complete. The zinc chloride produced at a mass of 10.7. Calculate the percentage purity of the zinc metal. And this is slightly more tricky, but is still a Mr. T question. So first work out moles. Now you can work out, because this zinc powder was impure, you can't work out moles using this number here, because the zinc powder is impure. There's other things in it that contribute to that mass, so we don't know what to divide by in terms of the MR. But we do know that this zinc chloride is pure, and it has a mass of 10.7. So that's what you're going to work out first, your moles of zinc chloride. That equals 10.7 divided by the MR of zinc chloride, which is 136.4. That gives you 0.0784. Then, that's in moles, then ratio. How much zinc, therefore, must have reacted? So moles of zinc will equal the same. The ratio is 1 to 1. So it's going to be 0.0784 as well. And then, therefore, what mass of zinc must have been in that impure zinc? We're going to multiply your 0.784 moles by the MR. So you use an appropriate triangle there. The MR is 65.4, and then equals 5.13. And then the percentage purity is going to be 5.13, so that's the pure zinc, divided by the mass of the impure zinc, which is 5.68, times 100, and that gives your answer, which is 90.2%. Predict the type of crystal structure in solid zinc fluoride and explain why its melting point is high. Zinc is a metal, fluorine is a non-metal, so you've got ionic crystal structure. And then explain why its melting point is high. There are strong attractions between oppositely charged ions. The final question, the structure of bromoalkane Z is this. Give the IUPAC name for Z. So, longest chain first. Got 1, 2, 3, 4. So that is going to be but. And there's no double bond, so it's butane. And then what have you got left? What's on this chain? So you got a methyl group, and a bromo. So bromo is alphabetically before methyl, so you're going to say where the bromo is. Well, you need to number your atoms either way. So 1, 2, 3, 4. So it's 2 bromo. And then you've got 2 methyl groups, one on the second and one on the third carbon. So then it's 2, 3, dimethyl butane. Give the general formula for the homologous series of straight chain bromoalkanes that contains 1 bromine atom per molecule. So you can use this as a guide. So you've got 1, 2, 3, 4, 5, 6 carbons here. So this is C6. And then how many H's you got? You got 3, 6, 9, 12. So H12 and then Br. I haven't got H12, sorry, you got another one here, haven't you? H13 Br. So this number here is 2 times this plus 1. So it's going to be Cn H2n plus 1 Br. And then it's just one reason why 1-bromohexane has a higher bonding point than Z. So this is because it's branched chain, so it has a smaller surface area. Sorry. Well, it has a higher boiling point than Z. Has a larger surface area. So stronger van der Waals forces between molecules. Then draw the display formula of 1,2-dichloro-2-methylpropane. So start longest chain, that's propane. Then add the other things. So 1,2-dichloro, so they're going to be there and there. 2-methyl. But remember, displayed means you need to draw all the bonds. I almost didn't there. So you have H, 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 H. All the bonds. And then state its empirical formula. We've got 3 C's. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 8 hydrogens and 2 chlorines. So C4H8Cl2. The empirical formula is you can divide all those by 2, so it's C2H4Cl. Make sure you always cross out any working you do for that, because they won't know which one you think is the empirical formula. If you have any questions on any of those questions that are in that paper, then please don't hesitate to email me.